Okay, we're gonna do something fun with circular motion, a classic banked turn. So what is a banked turn? So you've got two views here. As seen from above, your car is going to drive in a circle. Hey, since it's a circle, what does that mean? It means there's a centripetal acceleration here. Centripetal acceleration. Nice. Alright, so your side view, to keep your car going in there, you're going to have a banked turn like that. Now you've got some forces here. Don't worry about this drawing here. That's an extra one that I don't want to worry about yet. You've got gravity pulling you down, and you've got your normal force pulling you up. But these guys are not going to be equal to each other. But what you're going to have is you're going to have a net force. You're going to have a net force that points inwards. F net, because they're not going to perfectly cancel out. We know there's a net force because you're accelerating. You're doing centripetal acceleration. So that's what's going to be happening. Let's just jump in and do one. What's the max speed along a 15-meter turn with a 20 degree banking? No friction. We're not going to do friction today. Don't worry. That's tomorrow. Okay. So let's figure out this max speed. You'll notice mass doesn't matter. Alright, so let's draw a picture here. So there's a 15-meter turn. Here's my 20 degree banking. Here's the car. Here's the tail lights. Right, because you're seeing the back of the car here. Beautiful. Alright, let's draw the forces here. You've got gravity, so you've got mg. And you've got a normal force. And that's all you've got. That's all there is. There is no more. Now, gravity is diagonal, which is awful. We hate diagonal forces. I hate diagonal forces. So we're going to split it apart into the two components, parallel and perpendicular. We know our 20 degree angles right there. So, well, we don't know the mass, so we're just going to go with, how about mg cosine 20, mg sine 20. Ta-da! So far, so good. Okie dokie. Now, here's something else we know. We don't worry about the force normal right now, okay? So what do we know? We know that it is going to be accelerating this way, right? This is your FC. But your FC is also diagonal in reference to the slope here. So we are going to split your force of centripetal into two pieces. Like that. Are we okay with that? Hopefully. So far, so good. Hey. Alright, so one of these angles is 20. Which one is it? It is going to be, well, let me help you to see this here. This is going to be 90, right? I don't think that bothers you. If that's 90, that's 20, then these ones have to make 180, right? So your 20 is going to be over there, because this one is going to be your 70. Wait, 70? Yeah, 70. Alright, does that make sense? Because these two right here are parallel. So that's the way it adds up here. So I'm going to still keep in reference to 20 because that's what we're using here. So this guy right here is what we're worried about, because the only force that's going this direction is this one. The normal force is not going that way. So that means that this one is going to be mg sine 20. And this, the force centripetal, is the tangent version of there. So let's just think about this for a second. So you've got a triangle. It's looking like this. There's 20. You want to know what this side is. and you know what that side is. Well, you know that sine of 20 is going to equal y over x, right? Well, then you know that sine of 20 is going to equal mg sine 20 over fc. Are we okay with that? So far, so good? Hey. Oh. Hold on. This is a cosine. I promise I've done trig. Anyways, so solving for fc is going to equal mg sine 20 over cosine 20. And we just type this in the calculator. And if you really want to be fancy, mg tan 20. Alright? So, hold on. But we don't actually want to know what fc is. We want to solve for the velocity. So we're going to have mv squared over r, cross out the m's because they don't matter, multiply by the r, so we're going to get v squared is equal to tan 20. Alright, so we know 9.8, we know the radius is 15, we're multiplying it by tan 20, doing that to the square root, so we're going to get a velocity of 7.3 meters per second. Hey, and that's that. Alright, so the main idea for these is you have to break apart the forces. Your centripetal force is always going to point directly into the middle, so it's going to be horizontal, but you have to break it apart into the component form. That's the hardest part of this type of problem, right? Making sure you put the angle in the right place, unlike I did. Well, I guess I had a trig problem instead, but whatever. Okay, let's do another one. If you're feeling good, you can go ahead and try it on your own. Otherwise, don't pause the video if you're scared, and I'll help you out. What's the banking needed for a 12-meter turn with a speed of 16? Alright, so it's slightly different because, you know, you can just watch the video again if you want to see the same problem again. But, so same idea here. Here's your 12-meter turn. What kind of banking do you need? So we'll have that be a theta. And you've got a v is equal to 16. Alright, so this is going to be mg. It's not going to change a lot. So we're going to have, there's theta. So this is going to be mg cosine theta, mg sine theta. We're going to have a normal force, which we don't care about until tomorrow, and we're going to have a centripetal force, which goes out this way, Fc. Alright, so your centripetal force is going to have the two parts to it. I didn't draw that very well. Oh well. Okay, and since that's a theta, right? Same reasons that we talked about before, hopefully. Okay. This is going to equal mg sine theta. So what do I know? I know that fc cosine theta is equal to mg sine theta, right? I mean, if I didn't write it up here, you would just write fc cosine theta, right? But this guy has to equal this guy because they're the only forces that point that way. So there you go. Whatever, however you set it up, it's either way. All right, so we need to solve for the theta. So we're going to have to combine them together. Fusion, fc over mg is going to equal tan theta. Alright, so fc, we can figure out what that is. That's mv squared over r divided by mg. So the m's go away. V squared over r is equal to 16 squared divided by 9.8 divided by 12. So that's going to equal 2.18. and that's going to equal tan theta. Do the arctan of that. So 65 degrees. Nice. Do you like it? High banking, I suppose. I guess you're going really fast and you don't have any friction, so whatever. So that's what you're gonna do. Alright, let's do one more. What is the radius for a banking of 25 degrees at a speed of 24? Okay. Probably pretty big because it doesn't sound... Alright, pause the video, see if you can do this one now. Radius is r, v is equal to 24, 25 degrees, boom, 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 mg, boom, boom, 25, mg cosine 25, mg sine 25. I guess we don't even use the cosine. Normal force, which doesn't matter. 25, boom, 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 FC cosine 25. Alright, so FC cosine 25 is going to equal mg sine 25. Ta-da! Alright, what are we solving for? Oh, we gotta break apart FC. I'm gonna divide by the cosine while we're here. So we're gonna get mv squared over r is equal to mg tan 25. So cross out those m's. Multiply by r, divide by that stuff. V squared over g tan 25. And that's going to equal r. It's typing time! So v squared is 24 squared, divide by 9.8, divide by tan 25, and parentheses close. So we're going to get a 126. 126 meters. That's a big turn, which makes sense because you have no friction, so you're not going to turn very well. Okie dokie. Hopefully you had fun. We'll do some more tomorrow with friction.